Cancer risk evolution using a 5-dimensional radar model and topological geometry with a fluid VMT, plus TDA analysis of long-term cancer risk processes. Number 1470, VPT Sharp 031, December 18, 2025. Gerald C. EclaireMD Foundation. Category: Cancer, Fluid VMT, TDA Methodology. Preface: Why I study cancer risk without having cancer. I have written several papers on dementia and cancer, even though I do not have either condition. This was intentional, based on accumulated medical evidence and long-term systems observation. I believe that high percentages of late-life dementia risk and approximately 50 to 60% of all cancer risk are driven by metabolic disorders and lifestyle-related factors, rather than isolated organ-specific causes. Dementia and cancer are end-stage structural failures. My data focus on the long-term processes that cause or prepare those mortality failures. Introduction. Fluid dynamics perspective of disease preparation. Over the past 16 years, I have developed and refined Viscoplastic Medicine Theory, VMT, a physics-based energy framework that quantifies health through stress-strain relationships. This VMT methodology contains two complementary lenses: solid dynamics and fluid dynamics. More recently, I introduced Topological Data Analysis, TDA, a mathematics-based framework that describes how the geometric shape and connectivity of health data evolve over time. VMT measures how much internal strain energy is accumulated or released, while TDA describes how the system shape shifts, stabilizes, or bifurcates in geometric space. Together, VMT and TDA allow disease risk to be visualized not as isolated numbers, but as a living system evolving within a geometric landscape. Fluid VMT describes the long-term flow formation of cancer causes, while solid VMT captures the variance and final structural manifestation of cancer outcomes. This view is grounded in both published evidence and systems thinking. Late-life dementia is increasingly recognized as the downstream result of decades of metabolic dysfunction, vascular impairment, insulin resistance, sleep disruption, and chronic inflammation. Cancer follows a similar, though less dominant, pattern. Genetics and random mutations matter, but the internal metabolic environment strongly influences cancer initiation and progression. Chronic hyperglycemia, visceral fat accumulation, inflammation, and impaired immune surveillance create conditions that allow malignancy to emerge. Fluid VMT rationale. The dementia and cancer mechanisms described above are similar to my recent pontine stroke. That stroke resulted primarily from the cumulative effects of more than 30 years of type 2 diabetes, with about 91% of the damage originating from the first 20 years, from 1990 to 2009. This is analogous to heavy truck traffic slowly weakening a bridge. The acute trigger was a sudden hypertensive surge to 175 mm of mercury on June 21, 2025. In this analogy, the long-term metabolic burden represents the fluid VMT process, while the stroke itself represents the final structural collapse, captured by solid VMT. I do not have dementia or cancer outcomes in my dataset, and this is a strength rather than a limitation. My data capture upstream processes, long-term metabolic trends, lifestyle behaviors, continuous variation, gradual risk accumulation. These describe flow, not structure. For this reason, a fluid VMT interpretation is more appropriate than a solid VMT interpretation at this stage. Reinterpreting 5 input variables as flow. This reinterpretation does not require new data, only a different physical lens. 1. Glucose becomes fuel flow speed, rather than a static number of blood sugar. 2. Visceral fat becomes endocrine drag rather than fat storage. 3. Sleep becomes dead cell clearance and repair flow rather than rest. 4. Walking becomes oxygen and nutrient circulation support, rather than exercise. 5. Stress hormones become flow disruptors or acute shock triggers rather than emotional fluctuations. Viewed this way, cancer risk emerges as a long-term biomedical flow instability problem. 2 VMT methods and data. This study examines 18 biannual periods spanning 36 years from 1990 to 2025. 1 output strain is defined, cancer risk. 5 input stressors are used, obesity, type 2 diabetes, health age, diet, a combined stress and sleep. Each stressor is normalized to a 0.0 to 3.0 scale so that geometric shape, not raw magnitude, dominates this fluid dynamics interpretation. From a fluid VMT perspective, normalization allows each stressor to represent relative flow, resistance or recovery capacity within the same energetic frame. TDA radar geometry is fluid VMT's cross-sections. A radar chart becomes a geometric visualization tool. In this study, radar charts are used as cross-sectional snapshots of a multi-dimensional flow field. 3 representative biannual periods are selected. Y90-91 representing high strain, Y12-13 representing transition, Y24-25 representing low strain. Each polygon represents the instantaneous flow resistance profile, influencing cancer risk at that time. When stacked longitudinally, these radar slices form a 3D radar tube, representing viscoplastic strain evolution over time. In Y9091, the radar polygon is large and dominated by type 2 diabetes and diet. This reflects severe metabolic congestion, high internal drag, and maximum accumulated strain energy. In Y1213, the polygon contracts and becomes more balanced. All 5 stressors decrease, indicating partial energy release and improved flow stability. In Y2425, the polygon is smallest and most uniform. All stressors approach equilibrium, representing a low energy, stable flow state with minimal cancer risk preparation. Together, the 3 radar charts show a continuous shrinkage sequence: Y9091 high strain, Y1213 medium strain, Y2425 low strain. This geometric contraction mirrors the cumulative VMT energy reduction predicted by my VMT energy analysis. Topological interpretation. When TDA results interpreted longitudinally, radar charts become more than 2D plots. Each polygon is a time slice of a 6-dimensional functional space, composed of 5 stressors and 1 strain output. Stacked together, these slices form a continuous geometric surface and evolving path, creating a topological health manifold. Smooth transitions between polygons indicate gradual energy dissipation and recovery. Abrupt distortions would indicate bifurcation or pathological transition. In this dataset, the manifold is continuous and smooth. TDA construction, analysis, and observations. Each biannual period is treated as a point in 6-dimensional space. Euclidean distances between consecutive points measure geometric change over time. These distances form the foundation for TDA mapping, revealing data points, connectivity, stability, and potential bifurcation. The early period from Y9001 shows a broad, elevated surface dominated by diabetes and diet stresses. The largest geometric change occurs between Y0001 and Y0203. This marks the true turning point from cumulative stress accumulation toward recovery. After Y1213, geometric distances stabilize and manifold curvature flattens, indicating energy equilibrium and stable flow. The TDA results show that, within the observed data range, health changes progress along a single continuous path toward disease, without diverging into separate trajectories. This means the system evolved along one stable recovery trajectory, rather than splitting into alternative cancer risk outcomes. Combined fluid VMT and TDA conclusion. This combined fluid VMT and TDA analysis shows that cancer risk evolution is best understood as a continuous, time-dependent geometric process rather than a collection of isolated measurements. From the fluid VMT perspective, longitudinal radar charts represent interacting physiological flows. The gradual contraction of radar polygons reflects cumulative stress release, improved metabolic circulation, and reduced long-term biological load. These changes describe recovery as a process of flow stabilization, rather than structural repair. From the TDA perspective, stacking these longitudinal radar states forms a smooth topological health manifold. The analysis shows that health changes progress along a single continuous path toward disease or recovery, without bifurcation into separate trajectories. This confirms a stable, non-branching evolution pattern, consistent with fluid VMT predictions. Together, fluid VMT provides the energy-based interpretation of stress, accumulation and release, while TDA provides the geometric description of how the health system moves through state space over time. In essence, topological geometry can be viewed as a multi-dimensional radar chart, evolving continuously through time, linking physiological flow behavior with global disease trajectory. Core insight: cancer risk is not a sudden event. It is prepared over decades by disrupted flow, accumulated strain and stresses, and loss of internal coherence. Prevention is therefore not about fixing broken structures. It is about restoring and maintaining stable biomedical flow. This is the central message of fluid VMT plus TDA. Fluid VMT scope and interpretation. This study intentionally contains no solid VMT endpoints, such as tumor formation, tissue invasion, or irreversible structural damage. Instead, it focuses exclusively on upstream, metabolic and lifestyle-driven processes that precede disease. The data describe continuous flow behavior, gradual strain rate variations and stress-strain energy accumulation, and partial reversibility, which are best interpreted through a fluid VMT framework. Within this context, cancer risk is treated as a strain output arising from long-term biomedical flow instability, rather than as a structural lesion. The progressive contraction and increasing symmetry of radar geometries reflect reduced flow resistance and cumulative viscoplastic energy release, while the absence of bifurcation in the topological manifold confirms a stable recovery trajectory, without transition into irreversible collapse. Together, fluid VMT and TDA provide a systems-based explanation of cancer risk evolution that emphasizes prevention through long-term flow stabilization, rather than retrospective analysis of structural failure. Disclaimer: this content is provided for educational reference only, and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and related materials belong to the author, Gerald C.